GD&T for an injection molding program manager and project manager. The followings are summarized GD&T detail a program manager should know for he can communicate with all involved wisely. Why use GD&T instead of coordinate or conventional dimensioning? Coordinate or conventional dimensioning is easy to read and understand. It's the way most of us have learned to create drawings and is what we are familiar with. So, why make a change? Why would we not want to use simple plus or minus tolerances to locate features on a drawing? Because dimensioning the features of components using toleranced nominal dimensions had its limitations. For example, some components that were not manufactured to drawing and had therefore been scrapped or reworked, did in fact fit into their assemblies and function as intended. When it comes to the inspection of a part, GD&T has a great advantage over coordinate tolerancing. With coordinate tolerancing, dimensions of the part are given, but the drawing does not indicate how the part is to be set up for measurement. This can result in very different measurement values for the same part. So how does GD&T solve this issue? The answer: datums. A datum is a theoretical plane, axis, or point that are used to establish a datum reference frame that dimensional tolerances are referenced to. It is called out on a drawing as a capital letter with a box around it. Datums on a drawing show how the part is to be set up for measurement. You can use pictorial views for GD&T instead of two-dimensional views. Also, our industry today uses the Part 3D CAD data for CNC cut molds or dies and use 3D part CAD data with the CMM machine for measuring parts. For this reason there is no need for the 2D point-to-point coordinate dimensioning. Also perspective geometry is required for the 2D point-to-point drawings. Pictorial views with GD&T simplifies and reduce the number of dimensions requirements on the drawing. See examples below. As you can see in this GD&T pictorial drawing dimensioning, the drawing is clean and you can easily follow the dimensional requirements if you know GD&T. The red circles are used for mapping the dimensional report. This drawing shows coordinate dimensioning. As you can see, it can result in too many dimensions. It can lead to a massive miscommunications and dimensional inaccuracy if the part is slightly warped. Before proceeding further with GD&T, I believe all involved in injection molding must know the following for troubleshooting dimensional and cosmetic molding issues. 1. Know the industrial tolerance guide for the molded material and if necessary, consult with the material manufacturer for the recommended wall thickness. Dimensional tolerances, the material dimensional stability and behavior. The mold flow report can help you understand the part dimensional capability based on the part shape, material flow, gate location, and the cooling lines as designed in the mold. However, keep in mind that the material behavior is also a big factor for the required dimensions and the molding process can't correct the material behavior 100%. Understand the difference between precision manufacturing and commercial manufacturing. If the molding press used is not designed for precision manufacturing, don't expect good results for precision dimensions. Also know that the molding press barrel size with reference to the shot size has a big impact on the part dimensional results as you must use 25 to 65% for every shot. If you are molding thin wall parts, the injection molding machines for thin walled parts use high resolution microprocessors to control the thin wall injection molding process. It also required high-speed injection molding process and cycle time. The molding machines for thin wall parts are designed and built to withstand higher stresses and injection pressures. The molding machines' computer control are also designed for precision molding for thin wall quality parts. Thin wall plastic parts also depend on the flow length to thickness ratio of the plastic and the viscosity coefficient of the plastic. 2. Some product design due to their required functions or styles can still have significant challenges with regards to preventing warp in the injection molded parts. For example, injection molded housing with very large flat sides walls, with open top will have issues with maintaining their intended form and fit because the side walls deform or warp inwards. When checking a plastic part dimension, know if the part must be checked in free state or restrained. Keep in mind that the GD&T reference control frame is designed to tell you check the part restrained or in free state because the datums A, B and C are included in the reference control frame. If the customer wants you to check the part in free state, the reference control frame will include the free state modifier symbol, a circle with the letter F inside it next to the required tolerance. Restrained means the part must be clamped on the datum's free state. The part must sit on the datums but not clamped. Warped plastic parts will pass inspection and be functional if clamped to a condition that simulates the assembled or functional state. 3. Uniform wall thickness is critical in part design for an injection molded part. Non-uniform wall thickness causes dimensional control problems, warpage, and other part integrity issues. Parts with uniform walls thickness allow the mold cavity to fill more precisely since the molten plastic does not have to be forced through varying restrictions as it fills and quick part cooling. 4. If walls thickness are not uniform, the thinner sections cool first. As the thicker sections cool and shrink, stresses occur between the boundaries of the thin and thick walls. The thin section doesn't yield to the stress because the thin section has already hardened. As the thick sections yields, warping and twisting of the part occurs, which can cause dimensional and cosmetic issues. If design limitations make it impossible to have uniform wall thicknesses, the change in thickness should be as gradual as possible. Coring is a helpful method where plastic is removed from the thick area, which helps to keep wall sections uniform. Ribs and cord beads or folds as shown below in the color magenta, can also be designed into the molded part to increase stiffness and reduce the possibility of warping. To maximize this effect, the length and depth of the molded bead must be adapted to the size and thickness of the molded part. Limit the number of features that require side action, as some slides and lifters can be very small for a sufficient cooling circuit. Hot mold surfaces result in a long cycle time and warm parts. Warm parts result in ongoing warping and shrinking while parts are curing in the shipping or storage box. If molded parts are bulk packed, deformation can be a big issue if parts are warm because parts at the bottom of the box will bear all the weight and heat from the warm molded parts piled above it. Features that are designed in line with the die draw or mold opening can maintain an adequate cooling temperature if designed correctly. Remember that a molded part continue to cure and shrink for approximately 24 hours after molding. Do not use parts for dimensional reports if they are less than 24 hours old, as warm parts can result in an increased warpage and shrinking during the 24 hours curing time. These images show warpage with reference to the wall thickness, glass filled and heat. Know that plastic warp toward the hot surface. For appropriate draft, 1 to 2 degrees is usually acceptable, 3 degrees is optimal. 5. Texture, need 1 degree for every 1/1000th of an inch of texture depth on texture side walls. 6. Shut-off angle should be 3 degrees minimum. 5 degrees to 7 degrees is optimal. 7. Ribs should be designed to be 40 to 60% of the nominal wall thickness. A thinner rib does not provide much structure and may be hard to fill. Thicker ribs are tempting but will result in sinks marks on the cosmetic surface. 8. Minimize transitions from thick to thin. Areas where the wall increases in thickness are subject to warping and showing sink mark on the cosmetic surfaces. 9. Thin wall thickness increases injection pressure, and can result in short shot and many dimensional and cosmetic issues. Check with the material supplier to see if they have any specific thickness guidelines for the specific material you are interested in. Now I will talk about datums. A CMM holding fixture for a part like the one shown in this picture will have 3 datums A, B and C. There are generally 3 kinds of datum targets: points, lines, and areas. Points represent contact with spherical datum simulators. Lines represent contact with cylindrical datum simulators like dowel pins. Areas represent machine tooling surfaces. The rest is up to you. You create the fixturing scheme that will serve you the best. As you can see in this drawing, datum A is the bottom of the part, controls the part position up and down. Datum B is the side wall, controls the part rotation and across positions. Datum C controls the part position fore and aft. This page explains the 3 kinds of datum targets: points, lines, and areas. Datum reference frame, 3-plane concept. The concept of using mutually perpendicular features of a part to control its free movement in space, degrees of freedom. The 3-2-1 rule defines the minimum number of points of contact required for a part datum feature with its primary, secondary, and tertiary datum planes. It only applies when all three planes are used. The 3-2-1 rule says the primary datum feature has at least 3 points of contact with its datum plane. The secondary datum feature has at least 2 points of contact with its datum plane. The tertiary datum feature has at least 1 point of contact with its datum plane. The 3-2-1 rule only applies to planar datum features. Datum A is the primary datum. It controls the up and down position of the part and must have 3 contact points as shown in the picture. A1, A2 and A3. Translation along Z, rotation on axis X and rotation on axis Y. Datum B is the secondary datum. It controls the part cross-car location, rotation on axis Y and translation along X. Datum C is the tertiary datum. It controls the location of the part in the fore-aft position, minimum 1 contact points. Translation along Y. Most gauges or CMM holding fixtures are built to measure the molded part in body position or in its position in the assembly, and the datums are the fasteners' locations. A datum plane is a datum established on an external surface of a target. To use a flat surface as a datum, the following indication symbol is used. The surface of the target, datum feature, indicated as the datum, may be uneven or warped. Datum plane A can be established by supporting the surface set up as a datum using a surface plate or other higher precision plane. The supporting plane is the simulated datum feature. A simulated datum feature equals surface of surface plate. B datum equals plane set up by the surface plate. A datum center plane is the theoretical plane established on a center plane of the target. To use the center plane of two parallel surfaces as a datum, the following indication symbol is used. A simulated datum feature equals two flat contact surfaces. B datum equals plane set up by two flat contact surfaces. In the same way as a datum plane, the surface of the target, datum feature, specified as a datum may be uneven or warped. The datum center plane can be established by supporting the surface set up as a datum from both sides using precision planes. The two supporting planes are the simulated datum features. The theoretical plane generated from these features is the datum center plane. A datum line is the theoretical straight line established on the center of a cylinder bore or cylinder shaft, or a ridge such as the target's edge. A datum line can be a datum axis or datum axis line. A datum line is generally established on the center of a target's cylinder bore or cylinder shaft and is rarely established on a ridge. This section explains cases where a datum axis is established on a cylinder bore and on a cylinder axis. A datum axis line, equals axis line of maximum inscribed cylinder. B simulated datum feature equals maximum inscribed cylinder. The surface of the cylinder bore of the target specified as a datum feature, may be uneven or warped. By inserting a precision shaft that closely fits the bore, a datum can be established in this bore. Here, the inserted shaft is the simulated datum feature, and the axis line is the datum axis line. Datum axis, cylinder bore. A datum established on the center of a cylinder bore is indicated using the following symbol, as shown. Datum axis, cylinder shaft. A datum established on the center of a cylinder shaft is indicated using the following symbol, as shown below. A datum axis line, equals axis line of minimum circumscribed cylinder. B simulated datum feature equals minimum circumscribed cylinder. The surface of the cylinder shaft of the target specified as a datum feature, may be uneven or warped. By inserting the shaft into a precision housing that closely fits the shaft, a datum can be established in the housing. Here, the housing is the simulated datum feature, and the axis line is the datum axis line. A datum point established on the center of a spherical target is indicated using the following symbol, as shown below. A datum equals center of minimum circumscribed sphere. B simulated datum feature equals V block style 4 contact points, expressed by minimum circumscribed sphere. The spherical surface of the target specified as a datum feature, may be uneven or warped. When 4 contact points are made with 2 V-blocks, the datum feature sphere's surface is the simulated datum feature, and the center is the datum point. These 2 pictures shows the best practice to specify control to the AB axis. Red shows the location and orientation for the 2 tolerance zone to the AB axis. Facts you should remember for feature control frame. Geometric characteristic symbol. Diameter symbol, cylindrical tolerance zone. Stated tolerance. Modifier for the stated tolerance. Primary datum, 3 points minimum. Secondary datum, 2 points minimum. Tertiary datum, 1 point minimum. Basic sentence structure, when using the English language to say what is in the feature control frame. You may use the following connecting words. Example, the position of the feature axis must be within A.005. Tolerance zone at MMC relative to datum features A, B, and C. These are modifiers for the stated tolerance definition and the symbol for the feature control frame. MMC, maximum material condition. That condition where a feature of size contains the maximum amount of material within the stated limits of size. Example, minimum hole size and maximum shaft size. LMC, least material condition. That condition where a feature of size contains the least amount of material within the stated limits of size. Example, maximum hole size and minimum shaft size. Projected tolerance zone, when the symbol is shown, it means the stated tolerance zone is extended beyond the surface of the part, not within the part. Statistical tolerance, a tolerance for a part of an assembly based on the results from a statistical calculation. The desired result is larger tolerances. RFS, regardless of feature size, this is the default condition for all geometric tolerances. No bonus tolerances are allowed. Functional gauges may not be used. Datum symbol, this symbol is attached to a plane or size feature that must be contacted for machining and inspection. Basic dimension, these dimensions have no tolerance. They only locate a tolerance zone. Diameter symbol, this symbol replaces the word diameter. It should be used anywhere there is a diameter on the drawing, and when a tolerance zone is cylindrical. Tolerance zones, all tolerance zones shown in the feature control frame are total. Example, flatness within 0.004 means that 2 parallel planes no more than 0.004 apart define the tolerance zone. Datum targets, used to locate specific points, lines, or areas on parts used for support for machining and inspection commonly. Used on rigid parts like castings and forging and non-rigid parts made from plastic, rubber, or sheet metal. Limits of size rule, where only a size dimension is given. The size dimensions at any cross-section must be within the size tolerance. B. The surface shall not extend beyond the perfect form defined by the MMC size. C. The form may vary within an envelope between the MMC and LMC. The term limits of size refer to the 2 extreme permissible sizes for a dimension of a part, between which the actual size should lie. The largest permissible size for a dimension is called upper or high or maximum limit, whereas the smallest size is called lower or minimum limit. Pitch diameter rule, tolerances that apply to screw threads apply to the axis of the thread derived from the pitch cylinder. If another part of thread is to be used to derive the axis, it must be stated beneath the feature control frame. Any other feature that has a pitch diameter must have the datum feature stated. What is bonus tolerance? Bonus tolerance is the additional tolerance available for a geometric control attached to a feature of size with MMC, maximum material condition, and LMC, least material condition, modifiers. Bonus tolerance, when MMC is shown modifying a particular tolerance, the stated tolerance applies only when the feature being controlled is at MMC. The bonus is the difference between the actual size and the MMC size and may be added directly to the original tolerance. For example, as shown below, at MMC the hole must be positioned within a cylindrical tolerance zone of 0.005 of an inch diameter. As the example shows, the hole has departed from MMC by 0.03 of an inch. The 0.03 bonus tolerance may now be added to the original 0.05 zone for a total of 0.08 of an inch tolerance. In GD&T, bonus tolerance is a modification of a GD&T tolerance that under certain conditions increases the tolerance, hence the term bonus. More specifically, when the maximum material condition, MMC, symbol is used to modify a GD&T tolerance, bonus tolerance becomes available. The MMC modifier implies that the GD&T tolerance can be increased if the manufacturing process can control the related feature of size. As you can see in this second example of bonus tolerance as shown below. The top figure shows the drawing callout for the straightness of a cylindrical pin modified by an MMC symbol. The bottom drawing shows how controlling the feature of size can allow for more straightness tolerance. The logic here is if the feature of size is smaller than the MMC, then additional variation in the straightness should not prevent the successful assembly of this pin to its mating hole. For this reason, the manufacturing team may choose to intentionally make the part smaller in order to avoid the need to tightly control the straightness. Sometimes this leads to lower manufacturing costs since the part does not require special tools and equipment to control its geometry. This table shows examples of different results for the shaft measured straightness and the tolerance zone allowed for each result. What is maximum material boundary, MMB, is a boundary that the datum feature of size will not violate. The MMC size is the largest size, and the MMB is the boundary perpendicular to datum A and a diameter equal to the MMC size plus the perpendicularity tolerance. The figure below shows one example of a maximum material boundary. Below is an example of MMC and MMB for an external feature of size. The MMC size is the largest size, and the MMB is the boundary perpendicular to datum A and a diameter equal to the MMC size plus the perpendicularity tolerance. Pattern datums. The plate below has a surface that mates to another part. The 4 small holes locate the plate to the mating part by going over studs protruding from the mating part. The plate will go over all 4 studs at the same time and then sit flat on the mating part. The figure below shows one possible datum scheme, one that is used all too often. The mating surface is designated as the primary datum feature. That much is good. But then the designer chooses one of the small holes to designate as datum feature B and another one to designate as datum feature C. The 2 remaining locating holes and the large center hole are then located to A primary, B secondary, and C tertiary. This datum scheme implies that the holes designated as datum features B and C are somehow more important than the others. Since the holes are called out MMC and MMB, this also introduces unnecessary datum feature shift. The datum scheme simply does not reflect how the part functions. And most likely it does not reflect how the part will be inspected. The better datum scheme, the one that reflects how the part functions and how it should be gauged, is shown below. All 4 locating holes are designated as pattern datum B. The large center hole is then located to A primary, and B secondary. Everything is called out MMC and MMB because our only concern is assembly. When datum features are modified at MMB or LMB, the datum feature and the features being controlled may be able to shift relative to the datum axis or center plane. On the drawing shown below, datum feature B, in the position callout of the 4-hole pattern, is modified at MMB. This means the datum feature simulator for datum feature B would have a theoretical design size of diameter 19.6. Know that datum features can give you a shift, not a bonus. Since the actual datum feature could be produced as large as 20.2, the datum feature could shift as much as 0.6 total. This means the 4-hole pattern may shift out of position in one direction while the datum feature shifts in the other direction as shown. A very common error made at inspection is to use this allowed datum shift as a bonus on the features being controlled. This would allow the features to be out of position to each other more as the datum feature departs from MMB. This practice does not agree with the drawing or a hard gauge, should one be produced. What is a shift in GD&T, as a datum feature of size, that is geometrically controlled, departs from MMC? additional tolerance may be considered for the controlled features. This additional tolerance does not add directly to the original tolerance but must be applied to the pattern of features as a group. It is considered a tolerance that allows the controlled features to shift as a group. Datum shift refers to the available assembly clearance of a part when located in a fixture for gauging. Therefore, when a part with datum features not at mmB is placed on the gauge, it can be adjusted so that the features being measured are closer to nominal. Functional gauges, devices that measure the collective effects of size and geometric tolerances at the same time. It represents a simulated mating condition. Functional gauge, or attribute gauge, is an instrument that gives a binary pass/fail measurement result. Examples of attribute gauges include go-no-go plug gauges, slip gauges, and many visual inspection processes. They are tools used to determine if parts are manufactured within specified tolerance limits. A go gauge is intended to go inside the part feature being tested and it is manufactured with maximum material condition. Whereas no-go gauges are intended to not to go inside the part feature being tested and it is manufactured at least material condition. For example, when a 20 mm plus, minus, 0.1 mm hole is verified using go-no-go gauges. The go side pin is manufactured at 19.9 mm, hole mmC, and the no-go side pin is manufactured at 20.1 mm, hole LMC, along with the required tolerance limits. Following three conditions can arise while working with go-no-go gauges. Inspected part is OK or rejected depending on these three conditions. See the chart below. Bonus tolerances and functional gauges, directly applicable to any geometric characteristic that is modified by maximum material condition. Combination gauging with GD&T symbols. The true benefit of using the maximum material condition on a feature is the ability to call out GD&T with dimensional tolerances and be able to gauge for them at the same time. When geometric control and material control are used together, they form the true maximum envelope or virtual condition that the part can be in and still be to specification. For example, you have a pin with a dimensional and perpendicularity callouts. The pin needs to be within both perpendicular enough and small enough so that it doesn't get stuck when inserted into its mating hole at a 90 degrees angle to the face of the part. In this case, all you really care about is the pin fits into the hole at the worst case limits. MMC and maximum perpendicularity tolerance make up the maximum envelope of the part. The virtual condition can be controlled with a functional gauge. Functional gauges can be a huge benefit to production environments where measuring on the line quickly is critical. Reason for use. If you want to ensure that two parts never interfere or limit the amount of interference between the parts when they are at their worst tolerances, MMC can be called out. Take a shaft that must go through a hole with clearance between the two. The MMC of the shaft would be the maximum diameter, the MMC of the hole would be its minimum diameter. If you made sure that the MMC of the shaft was always smaller than the MMC of the hole, you guarantee there will always be clearance between the parts. This is important for any tolerance stack to ensure that when the tolerances are at their least desirable condition, the part still functions properly. Virtual condition, the collective effect of size and geometric tolerances that must be considered in determining the fit or clearance between mating parts or features. To calculate virtual condition, external features, MMC size and tolerance of form, orientation, or location. Internal features, MMC size, tolerance of form, orientation, or location. A virtual condition will exist only for tolerances that control size features. This is a good mathematical equation. For calculating tolerance feasibility, keep in mind that any number times itself is a positive number, or 0, so you can't ever get to a negative number by squaring. Since square roots undo squaring, negative numbers can't have square roots. Linear tolerance analysis. When analyzing a linear tolerance stack up, if you take the root sum square of your tolerances, there is a very good chance that the dimensional limits will fall within this zone. If you have just a few tolerances and you feel lucky, you can take the root mean square of your tolerances. RSS, root sum square. The square root of the sum of the square of the tolerances. RMS, root mean square. The square root of the sum of the square of the tolerances divided by the number of tolerances. On this page I am listing 4 of the GD&T symbols, how to use it and when to use datums and the required modifiers. Follow me to the next pages. I will give you enough information that will keep you in the loop during a product dimensional review. Straightness can refer to a surface or axis straightness. A surface straightness is the standard form of straightness is a two-dimensional tolerance that is used to ensure that a part is uniform across a surface or feature. Straightness can apply to either a flat feature such as the surface of a block, or it can apply to the surface of a cylinder along the axial direction. It is defined as the variance of the surface within a specified line on that surface. The tolerance zone, for a surface straightness are two parallel lines on either side of a surface line where the surface must lie. As shown below. An axis straightness is the form of straightness that controls the central axis of a part is sometimes referred to as axial straightness. This tolerance callout specifies how straight the axis of a part is, usually a cylinder. By definition, axis straightness is actually a 3D tolerance that constrains the center axis of the part, preventing it from bending or twisting too far. Maximum material condition further specifies this by controlling the size of the feature in addition to the allowed bend of the axis. Although a control of the axis, when MMC is called out, the entire part is used to determine if the tolerance has been met with a go gauge. The tolerance zone. For axis straightness, axis is a cylindrical boundary around the true central axis of the part, where the derived midpoint axis of the part must fit into. As shown below. Flatness is very straightforward. It is a common symbol that references how flat a surface is regardless of any other datums or features. It comes in useful if a feature is to be defined on a drawing that needs to be uniformly flat without tightening any other dimensions on the drawing. The flatness tolerance references two parallel planes, parallel to the surface that it is called out on, that define a zone where the entire reference surface must lie. Flatness tolerance is always less than the dimensional tolerance associated with it. The tolerance zone are two sets of parallel planes where the entire reference surface must lie. Circularity is a symbol is used to describe how close an object should be to a true circle. Sometimes called roundness, circularity is a two-dimensional tolerance that controls the overall form of a circle, ensuring it is not too oblong, square, or out of round. Roundness is independent of any datum feature and only is always less than the diameter dimensional tolerance of the part. Circularity essentially makes a cross-section of a cylindrical or round feature and determines if the circle formed in that cross-section is round. The tolerance zone are two concentric circles, one inner and one outer, in which all the points within the circular surface must fall into. The tolerance zone lies on a plane that is perpendicular to the central axis of the circular feature. As shown below, cylindricity is a symbol used to describe how close an object conforms to a true cylinder. Cylindricity is a three-dimensional tolerance that controls the overall form of a cylindrical feature to ensure that it is round enough and straight enough along its axis. Cylindricity is independent of any datum feature. The tolerance needs to be less than the diameter dimensional tolerance of the part. Cylindricity essentially forms a perfect cylindrical boundary around the object that the entire three-dimensional part must lie in. The tolerance zone are two concentric cylinders that run the entire length of the feature, one inner and one outer, in which all the points on the entire surface of the cylindrical feature must fall into. The entire length of the called-out feature would be controlled. As shown below, on this page I am listing 5 of the GD&T symbols, how to use it and when to use datums and the required modifiers. Parallelism, perpendicularity, angularity, profile of a line and profile of a surface. Follow me to the next pages. I will give you enough information that will keep you in the loop during a product dimensional review. Parallelism has two different functions in GD&T depending which reference feature is called out. The normal form or surface parallelism is a tolerance that controls parallelism between two surfaces or features. The surface form is controlled similar to flatness with two parallel planes acting as its tolerance zone. Axis parallelism is a tolerance that controls how parallel a specific part's central axis needs to be to a datum plane or axis. The axis form is controlled by a cylinder around a theoretical perfectly parallel axis. Parallelism is most commonly called out as surface parallelism. However, be sure to pay attention if it is referencing a central axis because it is different. We will only discuss surface parallelism on this page, but be sure to check out the page on perpendicularity to see how an axis is controlled with GD&T. Parallelism is a fairly common symbol that describes a parallel orientation of one referenced feature to a datum surface or line. It can reference a 2D line referenced to another element, but more commonly it relates the orientation of one surface plane parallel to another datum plane in a three-dimensional tolerance zone. The tolerance indirectly controls the 0 degrees angle between the parts by controlling where the surface can lie based on the datum. See the tolerance zone below for more details. Note, parallelism does not control the angle of the referenced feature, but only creates an envelope in which the feature must lie. It is important to determine what the reference feature is, surface or axis, and then what is acting as the datum, surface or axis, to determine how the parallelism is to be controlled. The tolerance zone are two parallel planes or lines which are oriented parallel to the datum feature or surface. All points that are on the referenced feature must in the tolerance zone. Remember, parallelism does not directly control the angle of the referenced surface, it controls the envelope, like flatness, where the surface needs to be. The goal is to ensure all points are within a specified tolerance distance away from their corresponding datum points. Perpendicularity of a surface and axis. Perpendicularity is a fairly common symbol that requires the referenced surface or line to be perpendicular or 90 degrees from a datum surface or line. Perpendicularity can reference a 2D line, but more commonly it describes the orientation of one surface plane perpendicular to another datum plane. The tolerance of the perpendicularity callout indirectly controls the 90 degrees angle between the parts by controlling the location where the surfaces have to lie. See the tolerance zone below for more details. Note, perpendicularity does not control the angle of the referenced feature. The tolerance is in distance units, millimeters and inches. The tolerance zone for perpendicularity of a surface. Two parallel planes or lines which are oriented perpendicular to the datum feature or surface. The planes are held perpendicular to the datum, but only ensure that the entire feature falls into the tolerance zone. Remember, perpendicularity does not directly control the angle of the referenced surface, it controls the envelope, like flatness, where the surface needs to be. Perpendicularity of an axis. Axis control can also be called out for perpendicularity and is one of the more common forms of axis callouts. When it is referenced for a circular feature, the feature control frame will contain the diameter symbol. Axis perpendicularity can be applied to a positive feature, pin and boss, or to a negative feature, a hole. When perpendicularity is referenced for axial control of a feature, the symbol now specifies a cylindrical boundary where the axis of the referenced feature must lie. This cylindrical boundary is formed by taking a line that is directly perpendicular to the datum feature. When this version of perpendicularity is called out, it is to be used with maximum material condition to enable easy gauging of the part. See example 2 below for how these particular parts are gauged. The tolerance zone is a cylinder surrounding a referenced theoretical axis which is directly perpendicular to the datum feature. The tolerance zone is the diameter of the symbol in which the central axis of the measured feature must lie. Angularity is the symbol that describes the specific orientation of one feature to another at a referenced angle. It can reference a 2D line referenced to another 2D element, but more commonly it relates the orientation of one surface plane relative to another datum plane in a three-dimensional tolerance zone. The tolerance does not directly control the angle variation and should not be confused with an angular dimension tolerance such as plus or minus 5 degrees. In fact, the angle, for now, becomes a basic dimension, since it is controlled by your geometric tolerance. The tolerance indirectly controls the angle by controlling where the surface can lie based on the datum. See the tolerance zone below for more details. Maximum material condition or axis control can also be called out for angularity, although the use in design and fabrication is very uncommon since gauging a hole or pin at an angle is difficult. When angularity is called out on an axis, the tolerance zone now becomes a cylinder around the referenced axis at an angle to the datum. The page on perpendicularity goes into this type of reference in further detail since it is more common with perpendicularity. The tolerance zone are two parallel planes or lines which are oriented at the specified angle in relation to a datum. All points on the reference surface must fall into this tolerance zone. Angularity does not directly control the angle of the reference surface, it controls the envelope, like flatness, that the entire surface can lie. Profile of a line describes a tolerance zone around any line in any feature, usually of a curved shape. Profile of a line is a two-dimensional tolerance range that can be applied to any linear tolerance. If it is called out on a surface, like a radius on a part, profile of a line would specify how much that cross-section could vary from a true curved radius. Profile of a line takes a cross-section at any point along the surface and sets a tolerance zone on either side of the profile. The profile of a line callout can also be set with an all-around leader or given a specific range. See example below. The tolerance zone are two-dimensional tolerance zone existing of two parallel curves that follow the contour of the true surface profile. The application on where the tolerance zone applies can be specified on the drawing. This tolerance zone may or may not be referenced by a datum. Profile of a surface describes a three-dimensional tolerance zone around a surface, usually which is an advanced curve or shape. If it is called out on a curved surface, like a eyelet on a welded part, the entire surface where the radius is has to fall within the tolerance zone. Profile controls all the points along the surface within a tolerance range that directly mimics the designed profile. Any point on the surface would not be able to vary inside or outside by more than the surface profile tolerance. Usually, when surface profile is required, there are no tolerances on the dimensions that describe the surface and use the GD&T callout to give the acceptable range. The tolerance zone is three-dimensional tolerance zone existing of two parallel surface curves that follow the contour of the surface profile across the entire length of the surface. This tolerance zone may or may not be referenced by a datum. On this page I am listing two of the GD&T symbols, how to use it and when to use datums and the required modifiers. Circular runout. Total runout. Follow me to the next pages. I will give you enough information that will keep you in the loop during a product dimensional review. Circular runout is how much one given reference feature or features vary with respect to another datum when the part is rotated 360 degrees around the datum axis. It is essentially a control of a circular feature, and how much variation it has with the rotational axis. Runout can be called out on any feature that is rotated about an axis. It is essentially how much wobble occurs in the one part feature when referenced to another. The tolerance zone is two-dimensional circular tolerance zone that is defined by a datum axis where all points on the called surface must fall into. The zone is a direct reference to the datum feature. Runout is the total variation that the reference surface can have when the part is rotated around the datum's true axis. Total runout is how much one entire feature or surface varies with respect to a datum when the part is rotated 360 degrees around the datum axis. Total runout controls both the amount of variation in the surface as the part is rotated, but the amount of variation in the axial dimension. Both radial variation and axial variation are measured and held within the tolerance. Total runout is usually called on a part that is rotated about an axis where the entire surface is critical to be in spec. The tolerance zone is three-dimensional cylindrical tolerance zone that surrounding a reference surface that is directly derived from either the datum surface or the axis. All points along the surface must fall within this zone when the part is rotated at all times. On this page I am listing three of the GD&T symbols, how to use it and when to use datums and the required modifiers. Position, concentricity, symmetry. Follow me to the next pages. I will give you enough information that will keep you in the loop during a product dimensional review. True position is actually just referred to as position in the ASME standard. Many people refer to the symbol as true position, although this would be slightly incorrect. The position tolerance is the GD&T symbol and tolerance of location. The true position is the exact coordinate, or location defined by basic dimensions or other means that represents the nominal value. In other words, the GD&T position tolerance is how far your feature's location can vary from its true position. Position is defined as the total permissible variation that a feature can have from its true position. Depending on how it is called out, true position can mean several different things. It can be used with max material condition, MMC, least material condition, LMC, projected tolerances, and tangent planes. It may apply to any feature of size, feature with physical dimensions like a hole, slot, boss, or tab, and control the central elements of these size features. In these examples, we will use holes, since these are the most common types of features controlled by true position. Position can be used on any feature of size, but not on surfaces where we would use profile. Position is probably the most widely used symbol in GD&T. The tolerance zone. True position location of a feature: a two-dimensional cylindrical zone or, more commonly, a three-dimensional cylinder, centered at the true position location referenced by the datums. The cylindrical tolerance zone would extend though the thickness of the part if this is a hole. For the three-dimensional tolerance zone existing in a hole, the entire hole's axis would need to be located within the cylinder. Gauging of an internal feature for the true position under MMC of a hole. Gauge diameter, pin gauge, equals minimum diameter of hole, MMC, maximum material condition minus true position tolerance. Locations of the gauge pins or holes are given on the drawing as basic dimensions. All gauge features should be located in the datum true positions but sized according to the formulas above. Note on bonus tolerance. When a functional gauge is used for true position, any difference the actual feature size is from the maximum material condition would be a bonus tolerance. The bonus tolerance for position then increases as the part gets closer to LMC, least material condition. The goal of a maximum material condition callout is to ensure that when the part is in its worst tolerances, the true position and size of the hole and pin will always assemble together. For instance, if you had a large hole size but was still in tolerance, closer to LMC, you make more bonus tolerance for yourself, making the true position tolerance larger. You can now have the hole center more out of position due to the bonus tolerance. This is an example of a 2D drawing for positional tolerance. This is an example of a 2D drawing for positional tolerance and gauge. Concentricity is a tolerance that controls the central axis of the referenced feature to a datum axis. The axes for the datum and referenced feature are derived from the median points of the part or feature. Concentricity is a very complex feature because it relies on measurements from a derived axis as opposed to tangible surface or feature. GD&T tolerance zone. Concentricity is a three-dimensional cylindrical tolerance zone that is defined by a datum axis where all the derived median points of a referenced circular feature must fall into. The median points of the reference surface cross-sections form the theoretical axis that must be in this tolerance zone. Concentricity is considered one of the most difficult GD&T symbols to measure due to its difficulty in establishing the midpoints of the feature. First, you must establish a datum axis which to measure. Once the datum axis is established, you must now take measure many a series of cross-sections, however many is realistic. Once the cross-sections are taken and the exact plot of the surface is obtained, the median points of these cross-sections must be determined. Then these series of points must be plotted to see if they fall within the cylindrical tolerance zone. This can only be done on a CMM or other computer measurement device and is quite time-consuming. When used, I don't recommend concentricity for molded plastic part. Use only for metal machined parts. Due to its complex nature, concentricity is usually reserved for parts that require a high degree of precision to function properly. Transmission gears, which need to always be coaxial to avoid oscillations and wear, may require concentricity to ensure all the axes line up correctly. Equal mass or inertial concerns are one of the leading causes for the concentricity callout. Any application where the median points of a feature need to be controlled relative to a datum would require cylindricity. However, in many cases, the use of runout or true position can replace the need for concentricity and be much easier to measure for. Symmetry is a three-dimensional tolerance that is used to ensure that two features on a part are uniform across a datum plane. An established true central plane is established from the datum, and for the symmetry to be in tolerance, the median distance between every point on the two surface features needs to fall near that central plane. Each set of points on the reference features would have a midpoint that is right between the two. If you take all the midpoints of the entire surface, this must lie within the tolerance zone to be in specification. Symmetry is not a very common GD&T callout since it has very limited functional uses. Centering location is done with position, and the verification and measurement of symmetry can be difficult. The tolerance zone are parallel planes on equal sides of a central datum plane. The median points of the symmetrical surfaces must all lie within this zone. Least material and concept. Least material condition is a feature of size symbol that describes a dimensional or size condition where the least amount of material, volume and size, exists within its dimensional tolerance. The callout also overrides GD&T regardless of feature size rule. For simplicity, if it is a whole or internal feature, LMC equals largest whole size, least material in part. If it is a pin or external feature, LMC equals smallest size of the pin. Least material condition is one side of the dimensional limits on a part. The other side of the tolerance range would be the maximum material condition. If you want to ensure that two always have contact or a press fit, least material condition can be called out. It is most often the control of parts that are pressed together to ensure that they always have a snug fit and no clearance. If you made sure that the LMC of the shaft was always larger than the LMC of the hole, you ensure that there will always be a tight fit between the parts. This creates a condition where you can use a functional gauge to ensure that the external feature is not too small or that the internal feature is too loose. Use in GD&T. Least material condition is fairly rare in geometric dimensioning and tolerancing. There are only a few reasons why a LMC should be called. The most common reason for calling it would be that you have a hole or other internal feature that is very close to the edge of a part. If you call LMC with true position in figure 2 below, you would be specifying that if the hole is at its largest size, it can only vary by as much as the true position tolerance. However, if the hole is smaller than its least material condition, you can apply a bonus tolerance to the part, because now the true center of the hole can be closer to the edge, without minimizing the thickness of the material. Concept of LMC with no-go gauges. The concept of the least material condition, not the GD&T symbol, comes in handy when a functional gauge is needed to control a part. If you want to limit the size of your feature to ensure a proper fit, you can specify the least material condition callout and control it with a specific type of gauge called a no-go gauge. For example, if you wanted to ensure that a pin always has a tight fit into a hole, you could design the no-go hole gauge to mimic the least material condition of the part. This would be a block with a hole of a diameter equal to the pin's LMC, min O. To check the part, you would try to insert the pin into the hole. If it doesn't fit, no go, then you know that the pin is large enough to be a tight press fit into the feature. A no-go gauge for a hole would use a pin gauge equals hole's maximum diameter. A no-go gauge for a pin would use a ring gauge equals pin's minimum diameter. Cannot combine gauging with GD&T symbols. Here is where the weakness of LMC comes out. In maximum material condition you are defining that the size cannot go past the max material size and the geometric callout. This works fine because you are using two tolerances that are positive. However, with least material condition this you cannot create a functional gauge that controls both. For example, if you have a perpendicularity callout and want to also control LMC on a hole, you can check the hole for size with a no-go gauge to ensure it is small enough for a press fit. However, If you specify a gauge that allows for a bonus tolerance on the least material condition, you cannot make a no-go gauge also check the perpendicularity, because a no-go gauge is designed not to fit. The problem is that GD&T symbols always specify the maximum amount that a part can vary and cannot be combined when you are controlling the least material control of size. The only way LMC can be called on a feature would be if the least material condition and the perpendicularity were measured and calculated separately. This, however, eliminates the benefit and speed of a gauge. For these reasons, least material condition is seldom used as a control for geometry and size. While gauging is always possible for least material condition size in a production environment, you cannot gauge for both GD&T and dimension at once. The takeaway should be that in GD&T, understanding least material condition as a concept of size is important. The only time you will truly see it is combined with true position on thin-walled parts, like in the thin wall hole example above. Notes: rare usage. Least material condition should only be used when absolutely needed, due to not being able to accurately gauge for size and geometry at once. Least material condition is really only used to ensure there is enough thickness between the edge and the inside of the hole. Features of size. Least material condition is one of three features of size callouts in GD&T. The other two are maximum material condition and regardless of feature size. All of these specify the condition that the part or feature must be in to apply the specified tolerance, regardless of feature size as default. When there is no callout to maximum material condition or least material condition, all parts default to regardless of feature size, meaning the geometric controls exist regardless of how large or small the part dimensions are. Maximum material condition, or for short, MMC, is a feature of size symbol that describes the condition of a feature or part where the maximum amount of material, volume/size, exists within its dimensional tolerance. The callout also removes GD&T rule number 2, which states that all geometry tolerances are controlled independently of the feature size. When you have a feature that GD&T is called on, if it is a hole or internal feature, MMC equals smallest hole size. If it is a pin or external feature, MMC equals largest size of the pin. The only GD&T symbols where max material condition can be applied are straightness, axis, parallelism, perpendicularity, angularity, true position, very common. Reason for use. If you want to ensure that two parts never interfere or limit the amount of interference between the parts when they are at their worst tolerances, MMC can be called out. Take a shaft that must go through a hole with clearance between the two. The MMC of the shaft would be the maximum diameter. The MMC of the hole would be its minimum diameter. If you made sure that the MMC of the shaft was always smaller than the MMC of the hole, you guarantee there will always be clearance between the parts. This is important for any tolerance stack to ensure that when the tolerances are at their least desirable condition, the parts still function properly. Gauging max material condition. Maximum material condition comes in handy when it comes to making a functional gauge for the part. If you want to limit the size of your feature, you can specify the max material condition callout. Additionally, control it with GD&T. For example, if you wanted to ensure that a pin always fits into a hole when the hole is at MMC, we could design a pin gauge that mimics the lower limit of the hole. The gauge that controls the max material condition of a part is called a go gauge, meaning the part must always go into it. The go gauge for a hole or internal feature would exist of a pin that is just a tiny bit, few microns, smaller than the maximum material condition of the hole. The gauge pin would then be inserted into the hole, and as long as the pin goes into the hole, the part is in spec. Note, the pin gauge may be made slightly smaller, a few microns, than the MMC to account for any straightness or tolerance issues that may be inherent in producing the gauge. Remember, when no GD&T is called on the hole, the envelope principle applies, meaning the geometric and size effects of the hole cannot be larger or smaller than the tolerances specified. Combination gauging with GD&T symbols. The true benefit of using the maximum material condition on a feature is the ability to call out GD&T with dimensional tolerances and be able to gauge for them at the same time. When geometric control and material control are used together, they form the true maximum envelope or virtual condition that the part can be in and still be to specification. For example, you have a pin with the dimensional and perpendicularity callouts. The pin needs to be within both perpendicular enough and small enough so that it doesn't get stuck when inserted into its mating hole at a 90 degrees angle to the face of the part. In this case, all you really care about is the pin fits into the hole at the worst case limits. MMC and max perpendicularity tolerance make up the maximum envelope of the part. The virtual condition can be controlled with a functional gauge. Functional gauges can be a huge benefit to production environments where measuring on the line quickly is critical. Gauging for MMC with geometric tolerances. For the gauging of a hole with perpendicularity callout. Gauge diameter, pin gauge, equals minimum diameter of hole, MMC, GD&T symbol tolerance, bilateral tolerance. Bilateral tolerance is the term used when the tolerance zone is distributed from the target value or true profile in both directions. Bilateral tolerances allow equal variation on each side of the target. Figure 1 below shows the GD&T notation for profile with a bilateral tolerance of 1 mm placed on the 15 mm radius. The tolerance zone for this case can be visualized as the space between the two concentric arcs shown in blue. By default, the tolerance is equally disposed about the true profile, meaning that 0.5 mm of variation is permitted in each direction from the true profile, 15. In this case, the inner blue arc would have a radius of 14.5 mm, and the outer arc would have a radius of 15.5 mm, and the measured surface of any part would have to fall within this tolerance zone, unequally disposed tolerance. Tolerance zones can also shift to allow variation to be larger on one side of the true profile. This is called unequally disposed tolerance. In GD&T, unequally disposed tolerance is indicated by an encircled capital letter U. The unequally disposed symbol is shown after the total tolerance number in the feature control frame as shown in figure 2 below. It is followed by a number indicating how far the tolerance zone extends outward from the true profile. This means that the number to the right is adding material. Say that we want to modify our example from figure 1 so that the minimum allowable radius of our arc is 14.4 mm. Since the true profile is a perfect arc with a radius of 15 mm and we will allow the actual surface to be 0.6 mm outside of that, the number 0.6 would follow the U symbol as shown in figure 2 below. In this case, the inner blue arc would have a radius of 14.4 mm, and the outer arc would have a radius of 15.4 mm. Profile, unequal and unilateral. The ASME Y14.41-2003 Digital Product Definition Data Practices Standard has given us a way to express several geometric tolerances. One of the most useful is the one for unequal bilateral and unilateral profile of a surface tolerances. In the interest of space, both methods of indicating unequal bilateral profile of a surface tolerancing on a drawing are illustrated. Both would not appear on a single drawing. Think of the detail view as the means this portion. According to the Y14.41 standard, the value that follows the U in a circle is the amount of tolerance zone that applies outward from the surface. This may also be used to indicate a unilateral profile tolerance. Unilateral tolerance. Unilateral tolerance is a type of unequally disposed tolerance where variation from the true profile is only permitted in one direction. GD&T notation for this is identical to unequally disposed tolerance, with the number trailing the U symbol either 0 or equal to the tolerance amount. As you may have learned, it is good practice to design parts at maximum material condition, or MMC. MMC means using the largest possible pin or smallest possible hole within the tolerance zone. Unilateral tolerance allows us to specify tolerances in a way that matches the thought process of this design. Using the same example from figure 1, we apply this concept to figure 3 below. We want the MMC size of our radius to be 15 mm, which is the basic radius dimension, so we will add 0 to the right of our U symbol. This means that the tolerance zone will be distributed to the inside of the feature and cannot get any smaller than 15 mm but can get as large as 16 mm. Let's look at one last scenario. What if we didn't want the radius to get any larger than 15 mm? As shown in figure 4 below, if we add 1 to the right of the U symbol, our tolerance zone will only be distributed to the outside of the true profile. Remember what we stated earlier, the value to the right of the U symbol adds material. Therefore, our radius can never be larger than the basic radius dimension of 15 mm, but can get as small as 14 mm, which would now be the MMC size. Another reason for using unilateral tolerances is to shift the statistical variation of parts toward one end of the allowable range. If a manufacturer is making parts to a drawing with an equally disposed bilateral tolerance, we expect the distribution to be centered about the true profile. However, if we find that the parts fit better at MMC, creating a better quality and longer lasting assembly, we could switch the bilateral profile tolerance over to a unilateral profile tolerance to communicate that to the manufacturer. Key takeaways. Bilateral profile tolerance means variation from the true profile is permitted equally in both directions. Unequally disposed profile tolerance means that more variation from the true profile is permitted in one direction than the other. Unilateral profile tolerance means that variation from the true profile is permitted in one direction only. The following 3 pages summarize the previous 5 pages. Example 1, as shown in this picture, the profile of surface tolerance applies unilaterally away from the port when located on datums A, B, and C. The 0.3 following the unequal symbol indicates the amount of the tolerance zone outside of the material. Profile of surface tolerance applies bilaterally with an unequal distribution. The 1 following unequal say part when located on datums A, B, and C. The 0 following the unequal symbol indicates the amount of the tolerance zone outside of the material. Profile of surface tolerance applies bilaterally with an unequal distribution. The 1 following unequal symbol part indicates the amount of the tolerance zone outside of the material. This is another calculated value the program manager and a project manager must get familiar with and make sure the quality engineers follow the criteria for the required numbers correctly for a good manufacturing process. Process capability, CP and CPK, and process performance, PP and PPK, what is the difference? Definitions. CP is process capability. A simple and straightforward indicator of process capability. CPK is process capability index. Adjustment of CP for the effect of non-centered distribution. PP is process performance. A simple and straightforward indicator of process performance. PPK is process performance index. Adjustment of PP for the effect of non-centered distribution. CPK equals half means you've crunched nearest the door edge, ouch. CPK equals 1 means you're just touching the nearest edge. CPK equals 2 means your width can grow 2 times before touching. CPK equals 3 means your width can grow 3 times before touching. Ongoing process performance requirements are defined by the customer. If no such requirements have been established, the following default values apply. For stable processes and normally distributed data, a CPK value greater than or equal to 1.33 should be achieved. For chronically unstable processes with output meeting specification and a predictable pattern, a PPK value greater than or equal to 1.67 should be achieved. All processes must produce all characteristics to specification on a production basis. Significant characteristics, SCS, must be in a state of statistical control with PPK greater than or equal to 1.67 and CPK greater than or equal to 1.33. Finally, within the production part approval process, PPAP, Manual, AIAG, 1995, the requirements that relate to process capability are given as follows. Calculate the PPK index and take the following actions. For processes that appear stable, PP and PPK greater than 1.67, the process probably meets customer requirements. After approval, begin production and follow the approved control plan. 1.33 less than or equal to ppk less than or equal to 1.67. The process may not meet customer requirements. After part approval, begin production with additional attention to the characteristic until an ongoing CPK greater than or equal to 1.33 is achieved. ppk less than 1.33. The process is substandard for meeting customer requirements. Process improvements must be given high priority and documented in a corrective action plan. Increased inspection or testing is normally required until an ongoing CPK of 1.33 is demonstrated. A revised control plan for these interim actions must be reviewed with and approved by the customer. Processes that appear unstable at the time PPAP approval is sought require special attention, until ongoing stability and CPK of 1.33 is demonstrated. Gauge RNR, which stands for Gauge Repeatability and Reproducibility, is a statistical tool that measures the amount of variation in the measurement system arising from the measurement device and the people taking the measurement. When measuring the product of any process, there are two sources of variation: the variation of the process itself and the variation of the measurement system. The purpose of conducting the GRNR is to be able to distinguish the former from the latter, and to reduce the measurement system variation if it is excessive. If the percent gauge RNR is under 10%, the measurement system is generally considered to be an adequate measurement system. If the percent gauge RNR is between 10% to 30%, the measurement system may be acceptable for some applications. If the percent gauge RNR is over 30%, the measurement system is considered to be unacceptable. Gauge RNR per MSA standards: gauges must be able to achieve a gauge RNR and achieve an RNR value of 10% or less at gauge vendor location and at the production facility. A 3-operator, 3-trial and 10-part RNR study is the normal procedure for testing the gauge repeatability and reproducibility. A CMM gauge RNR study must have at least 2 points in each direction of the part. If there are any SBC points in any direction, they must be included. If there aren't any SBC points at the direction, the gauge builder, the OEM, and your quality manager must be involved in selecting the required 2 critical points based on the understanding on the GD&T drawing. Non-CMM gauges: for non-CMM fixture type of functional check gauges, gauge supplier is not required to supply GRNR unless the OEM and your quality manager requires otherwise. More or less. OEE is a Ford term for overall equipment effectiveness. Ford expect their suppliers to measure their equipment according to their defined method. 1. % of acceptable product, 2. % of expected cycle time actually achieved, and 3. Availability, or uptime percentage. For example, if your product is running 5% defects, 95% acceptable, the actual cycle time is 55 seconds when it should be 60, 92% of expected, and the line is down for 20 minutes in a typical 480-minute, 8HR, day, or 95% uptime. Then the OEE equals 0.95 multiplied by 0.92 multiplied by 0.96 equals 84%. Overall equipment effectiveness, OEE, is a measure of how well manufacturing operation is utilized, facilities, time, and material, compared to its full potential, during the periods when it is scheduled to run. It identifies the percentage of manufacturing time that is truly productive. An OEE of 100% means that only good parts are produced, 100% quality, at the maximum speed, 100% performance, and without interruption, 100% availability. By measuring OEE and the underlying losses, important insights can be gained on how to systematically improve the manufacturing process. OEE is an effective metric for identifying losses, benchmarking progress, and improving the productivity of manufacturing equipment and eliminating waste. Measuring OEE is a manufacturing best practice. Total Effective Equipment Performance, TEEP, is a closely related measure which quantifies OEE against calendar hours rather than only against scheduled operating hours. A TEEP of 100% means that the operations have run with an OEE of 100% 24 hours a day and 365 days a year, 100% loading. Run at rate is the GM term for an audit of the process, including investigation of the ability of the supplier to meet the capacity required. This is called 2-day production by VW. According to QCI's Quality Dictionary, is verification that a production process is capable of producing the desired quality at quoted rates. What is a composite tolerance? A composite tolerance is indicated by two lines with a single tolerance of position or profile symbol. A composite tolerance is always applied to a pattern. In a composite tolerance, the top line controls position. It would control orientation also if there were no bottom line. Bottom line controls spacing between the components in the pattern and orientation of the pattern relative to datums. The bottom line never controls location relative to a datum. The tolerance zones for composite tolerance as shown in this picture. A composite tolerance specifies two tolerances for the same geometric characteristic of a feature or for features that have different datum requirements. One tolerance relates to a pattern of features and the other tolerance to each feature within the pattern. The individual feature tolerance is more restrictive than the pattern tolerance. In the following illustration, the point where datums A and B intersect is called the datum axis, the point from which the position of the pattern is calculated. A composite tolerance could specify both the diameter of the pattern of holes and the diameter of each individual hole, as in the following illustration. When you add composite tolerances to a drawing, you specify the first line of a feature control frame and then choose the same geometric characteristic symbol for the second line of the feature control frame. The geometric symbol compartment is extended over both lines. You can then create a second line of tolerance symbols. A multiple single segment tolerance is a tolerance of position callout or a profile callout, with two or more lines. Each line has a separate symbol. Each line is independent. Each line controls position and/or orientation to the specified datums. Multiple single-segment tolerances have only one rule. Rules for multiple single-segment tolerance. One datum references and datum modifiers in the lower segment must not be the same, and in the same order as those in the upper segment. In some cases, composite tolerances and multiple single-segment tolerances will have different meanings as shown below. In some cases, composite tolerances and multiple single-segment tolerances will have the same meaning as shown below. The following pictures show 3D GD&T. It is the new way the USA OEM wants to dimension part for better understanding of the dimensional requirements.